Ashwin, could
Hello,
you?
everyone. Welcome to the 2025 International Mission to Mars Design Engineering Competition. We are starting the competition round today with Team Solace. Team Solace, please go ahead and share your presentation, and you have the floor.
Thank you so much. Could you go to the previous slide, please? Yeah, thank you. Sampurna Vishwam Gantavyamasti Mangaladharabhyate, meaning the whole universe is to be visited beginning with Mars. Judges, scientists, mentors, and fellow explorers. It's time to land on Mars with our crew, Solace. And keep your eyes open. Imagine standing in the rust red soil, the sky a tinted peach, two moons rising. Tough, isn't it? But also beautiful. But we are here to help you understand your sustainability on our next home, Mars. Stick with us for the next 20 minutes to discover the future that we plan to build. This is the amazing team that worked behind our project. Here is a short summary of what our presentation will encompass. Here is the approximate timeline for our 1.5-year mission to Mars. We have ensured that there are buffer periods within each section and that the crew is trained to handle any contingency. Mission control will be responsible for any rescheduling if needed. Now, I'll hand it over to Trisha to talk more about science.
Our base, located in Deuteronolis Mensae, specifically at 44 degrees north and 23.375 degrees east, is a premier landing site, offering critical in situ resource accessibility via shallow, extensive subsurface ice and unparalleled scientific exploration potential across astrobiology, paleoclimate, and geology. Its mid latitude location ensures consistent solar insolation and mitigates environmental extremes, supporting missions with a 200 to 500-kilometer operation radius for maximized scientific return. Now, let's explore our science section, the unique brains of this mission. Deuteronomus Mensae is critical for understanding Mars's paleoclimate and volatile history, featuring extensive lobate debris aprons with 80 to 90% pure water ice. These deposits can reveal trapped gases at potential biosignatures and also serve as an invaluable in situ resource for human colonization. Detailed analysis of these ancient ice layers offers unparalleled and chronological data on Martian climate and atmospheric evolution. Furthermore, the sheer volume and accessibility of this water ice makes Deuteronomus Mensae a prime candidate region for future human landing site and resource utilization efforts. Here you can see some of the areas identified within a 200-kilometer radius around a landing site that are suitable to accomplish our scientific goals. A core mission objective is the direct investigation of potential past and or present Martian life and habitability, crucial for enabling human survival. This utilizes comprehensive geochemical and advanced organic and microbial detection instrumentation like ALF, Sherlock, pixel, and DNA or RNA sequencers. Experimental methodologies encompass perchlorate mitigation using engineered organisms called GMOs. Martian botany studies for carbon dioxide and oxygen production, and integrated sample analysis protocols for astronaut led investigations with strict sterilization. Cultivating plants on Mars faces significant hurdles, including nutrient poor perchlorate laden regolith, extreme temperatures, abrasive dust, and high radiation. Adaptive strategies involve careful selection of resilient crop species and advanced genetic engineering for perchlorate tolerance, enhanced radiation resistance, and efficient nutrient acquisition. Furthermore, engineering beneficial microbes for in situ resource utilization offers promising avenues for bioremediation and nutrient cycling. All these innovative approaches must be rigorously validated through crucial in situ experiments on the Martian surface to ensure their efficiency and sustainability for long term human presence. Ensuring long term crew health and mission success on Mars necessitates quantifying physiological adaptations to 0.38 grams of gravity, evaluating the nutritional and safety profiles of Martian grown crops, determining the Martian soil's circadian impact on human physiology, and comprehensively assessing deep space radiation exposure to develop robust protective countermeasures. Here are the mass breakdown tables for human effects, which include subcomponents, instrument, and approxims. Now, handing it over to Kashvi.
A Mars mission features three critical research programs for human colonization. First are InSight resource utilization experiments, which are the foundation of Martian self sufficiency. We'll be extracting subsurface water ice through rotary drilling, converting toxic percolates into valuable oxygen while detoxifying soil and recovering water from clay minerals. We'll also be manufacturing regolith bricks and transforming the Martian dust into functional glass, which will dramatically reduce our dependence on Earth supplies and establish a sustainable infrastructure. A Martian rodent research program represents the humanity's first multi generational mammalian study under 0.38 G gravity. Using 60 mice across 4 generations, we'll be studying psychological effects which are impossible to research ethically on humans. Under strict ethical oversights, MARO will provide irreplaceable data on long term organ regeneration, genetic effects, radiation exposure, pharmaceutical efficiency, and Martian food safety, which are all essential for permanent human settlement. This is just the mass breakdown table for everything that will be used in the MARO experiment. Beyond the core research, we'll be leveraging Mars' unique environment for innovative discoveries. The bubble ballet studies fluid dynamics as soap bubbles freeze mid-air in the Martian atmosphere. Frisbee golf demonstrates altered ballistic under low gravity, while regolith canvas and controlled dust devils reveal crucial dust behavior and particle dynamics. Advanced experiments include paper airplane aerodynamics in ultra thin atmosphere, sonic canvas for acoustic data, and electrostatic dust ballet for safety protocols. Our fluid artistry experiments examine liquid behavior under partial gravity. Together, these represent humanity's most comprehensive mass investigation, providing essential data for sustainable human presence. These tables are the mass breakdowns for the experiments, stating the name, the components, and the general mass for every component. This is another mass breakdown table for all the general science instruments. Thank you.
Now, let's move on to engineering, the beating heart of our mission. We have worked to make everything new and better than our most already existing designs. Each topic has unique points that make this stand out. Let me start with our primary energy source, the Fission Surface Power System, or FSP, based on NASA's Kilopower reactor. It's a compact nuclear reactor using enriched uranium 235. Heat is transferred by coolant to a Brayton cycle turbine, generating about 40 kilowatts of continuous power. This energy is stored in batteries and distributed among the habitat and modules, providing stable, weather independent power. Though still under development, FSP offers the reliable baseline energy we need for long term Martian missions. The chart here shows energy consumption by each module. While the FSP is our main power source, we have also included solar panels as both a backup and a way to reduce the FSP's workload. We are carrying 14 deployable arrays, each generating 1.5 kilowatts, adding to a net 21 kilowatts. During the day, these panels help offset power needs and charge our battery banks. They will be cleaned by robotic attachments or will be cleaned manually. This means that even if the FSP needs maintenance or if a dust storm rolls in, we have got stored energy ready to power essential systems. What makes the system robust is that it's modular, adaptable, and designed with redundancy in mind. We also keep the battery units thermally regulated to prevent freezing at night when Mars can dip to minus 125 degrees Celsius. Here's the mass breakdown for the power generation units. To prevent contamination of Mars, our FSP is housed in a specifically designed multi-layered biocontainer, placed 25 to 30 feet from the habitat in a protective pit. This is something we would like to highlight. This is something which is often overlooked. The container includes beta cloth for UV and abrasion resistance, Vectran or Kevlar for puncture protection, aluminized captain to seal gases and block microbes and radiation, Teflon for chemical stability and clean separation. This ensures the FSP remains fully contained during transport and setup, meeting planetary protection protocols. One of our most unique contributions is Crystal Haven, a radiation shielded dome around the entire habitat. It's built with aluminium oxynitrate, and high-density polyethylene panels, which block up to 35% of cosmic rays and over 90% of solar radiation. There's also a circulating water layer that adds another 15 to 20% protection, helps control temperature. The excess heat from the FSP will be used to prevent the water from freezing by using a simple connection. What's more, we use local margin regolith to form a thick berm around the base. Altogether, Crystal Haven is not just a structure, it's a safe, self sufficient, and human centered home on Mars. My teammate Rayansh will now continue.
The MEXS Mark 7 keeps astronauts safe and mobile on Mars. It uses Nomex, Gore-Tex, Kevlar, and multi-layer insulation to handle dust and temperature swings, keeping pressure stable at 40 kilopascals. Veteran gloves help with dexterity. Astronauts will also wear observancy garments for hygiene. A wrist interface linked to an internal mic keeps comms clear even in emergencies. A helmet will be impact resistant with a heads up display and AI voice guidance. Life support runs automatically, managing oxygen, CO2, and temperature, while real time health monitoring adds safety. Finally, a lightweight exoskeleton in titanium alloys and carbon fiber cuts fatigue and prevents falls. The habitat blends rigid models for protection, like an emergency shelter, sanitation units, medway, exercise station, and airlocks with inflatable modules to save mass. Inflatables include a greenhouse, private sleeping pods, labs, and movable workstations. At the center is the common area, where the crew cooks, eats, and relaxes, which really keeps the morale up. Each inflatable expands about five-fold on Mars, adding around 40 square meters of space. There's also a special shielding module up to 60% more effective that can double as a vault or quarantine zone. Together, it feels safe, flexible, and human. This is a blueprint of what a habitat would look like. This has been made carefully, considering contingency, radiation protection, and convenience. We store water in a 2000 to 3000 liter tank with a carbon fiber shell and HDPE bladder. An aerogel blanket keeps it from freezing. Water moves through freeze-tolerant tubing powered by pumps and valves, reaching every module. The system weighs about 540 kilos, light enough to launch, big enough for the mission. At first, we bring water from Earth, but later we'll harvest Martian ice. Planned upgrades include UV LED disinfection and self-sealing EVA bags. ISRU uses Mars' own resources instead of shipping everything. Robotic drills harvest subsurface ice for drinking water, oxygen, and shielding Mars. We also pile 1 to 1.5 meters of local regolith around the habitat to block cosmic rays and solar storms, especially from the horizon. This cuts mass and cost, adds local backups, and turns Mars from a short visit into a place astronauts can truly stay. Ria, the stage is now yours.
Our mission's ground operations rely on the unpressurized rover built as rugged and autonomous workhorse for exploration and sample collection. It's based on the proven rocker boogie suspension, upgraded with metallic string tires for better durability on sharp rocks and sand. While real rovers crawl at less than 1 kilometer per hour, ours combine advanced AI and drone assistant navigation to safely reach an average speed around 5 to 10 km per hour. So it covers more ground each day. Power comes from our next generation advanced Stirling radioisotope generator, giving steady power day and night, independent of sunlight. But its real strength is its AI. It can navigate through tough terrains, reach scientific targets, and run onboard analysis, making it a tireless field geologist that keeps working long even after the crew heads home. Now, so here's a quick look at our mass of our unpressurized rover. It is distributed on. For long human missions, we rely on pressurized rover, which has workspace of a habitat attached to it. It carries a crew of 3 for multi-week trips and can reach a normal speed of 20 km per hour. Inside, there's a fully closed loop life support system that keeps the cabin at 8.2 psi. This pressure isn't random. It cuts down the time astronauts need to pre-breathe before going on an EVA. Power comes from a regenerative fuel cell, which uses hydrogen and oxygen to produce electricity and water, creating a sustainable cycle. For a 400 kilometer mission, it needs about 3,000 kilowatt hours of energy. It's far more than just transport. It's about moving lifeline that keeps the crew alive and productive on the Martian surface. And here's the mass breakdown of our pressurized rover along with its main components. The AD Scott 1 is a built heavy lift octocopter with modular structure, so it can adapt to different mission needs. It is powered by a regenerative hydrogen-oxygen fuel cell system backed up by lithium-ion batteries for steady energy during flight. This instrument suite can analyze temperature, soil and gas composition, topography, magnetic fields, and radiation, giving critical data to help plan future exploration and understand Mars better. It uses 3 to 5 kilovolts of energy, stays airborne to roughly 2 to 3 hours, and can carry payloads up to 10 to 15 kilograms. What makes it really versatile is its hybrid capability. It can switch to wheeled ground travel, so it keeps gathering even after landing. Here's the mass of our drone is distributed across its different parts and subsystems. Redwater System by Honeybee Robotics is an automated platform that drills and extracts water right on Mars, making ISRU practical and giving the habitat a sustainable water source. It uses coiled tubing drilling, followed by road well extraction to pull water efficiently from deep underground. The whole system rides on a self-driving vehicle with robotic gantries, running drilling and water collection almost fully autonomously. It only needs about 10 to 15 kilovolts per well, so it's energy efficient too. An onboard AI adjusts drilling parameters in real time. Once water is extracted, it's purified through a multi-tier process to make it safe for usage. And here's the overall engineering mass breakdown showing each part and subsystem in detail. Now inviting Nasif to talk us through the human operations.
Our rigorous merit-based crew selection targets diverse candidates aged 26 to 36. This three-stage process based on NASA ESA procedures narrows 30 initial contenders through simulations and training. The final 6% crew, 2 male, 2 female, 2 merit assigned, is selected for optimal psychological profiles and varied perspectives, ensuring mission success. Our mission roles and hierarchy ensures efficiency and redundancy within our 6% crew. While democratic, the commander holds final authority. All crew members share universal basic skills, engineering, first aid, maintenance, and shared responsibilities. Specific tasks include scientific documentation, landing vehicle piloting, cooking, and surface driving. Redundancy is key. The second medic in command and secondary medic are cross-trained to ensure mission's continuity. Our schedule is built on a 4 to 5 day Alpha Bravo team rotation, allowing dedicated high-intensity EVAs for one team while the other focuses on habitat maintenance and lab science, minimizing fatigue and boosting productivity. The daily timetable has two main work blocks balanced by time for breaks, team bonding activities, and personal reflection or family communication. Now, I'll hand it over to Lux to explain the rest of our human operations. Thank you.
Maintaining medical and psychological health is critical. Health challenges like nutritional deficiencies are countered by strict dietary planning, early detection, and physical activity. Our strategy includes daily health monitoring using samples, vitals, and sometimes even cognitive assessments and ultrasound. The robust medical wellness support, including journaling and regular checks. We also have a 3-day quarantine for illness. A pre-return protocol featuring full psychological and VR debriefing ensures readiness for Earth. Our self-sufficient Martian medical operations are crucial for our mission safety, prioritizing autonomy along with Earth oversight. The crew medical officer and second medic in command receive doctor-level training, while all others are combat medic trained. AI-supported diagnostics further enhance immediate response capabilities. The Smart Medbay, a central advanced facility, continuously monitors crew health via wearables and features a lab on a chip for rapid diagnostics, portable ultrasound, and contained MRI X-ray. All test results will be shared to human mission control. One thing I would like to add is that in our main habitat, 2 modules will be used from the landing vehicles, as in the landing vehicles will be 2 of the modules used in the habitat. Now, let's cover Martian agriculture, hydroponic sustainability. As you can see from the table, we'll cultivate crops like spirulina, microgreens, potatoes, and quinoa, selected for their nutritional value, fast growth, and high yields, ensuring a diverse yet balanced diet for the crew. Hydroponics offers numerous benefits for Martian agriculture. It saves water, it's space efficient, it allows us to maintain a controlled environment, and also for nutrient optimization. This leads to higher yields and ensures a closed loop recycling. Further, to ensure crew survival and to prepare for contingencies, we have ensured that the crew carries enough dehydrated food such that it is enough to last the entire mission. But we will still be using hydroponically grown food while the dehydrated food is stored for emergencies and rover journeys. Crew harmony and contingency planning is vital. For contingencies, the astronaut death protocol involves respectful storage. Anything after that will be done based on instructions from mission control. Regarding supplies and resources, astronauts consume 2,800 calories and 3 to 3.5 liters of water daily, sustained by hydroponics and water recycling. Crew selection prioritizes psychological strength, but conflict resolution will follow a three-step process, as mentioned. Next slide, please. This is the final slide of our presentation, and the table shows and explains the mass breakdown of operational factors, essential and miscellaneous, covering both our astronauts' needs and wants. Thank you so much for your time. We have successfully traversed through the challenges and triumphs, the innovations and inspirations that define our vision for Mars. This isn't just about designing a mission, it's about defining our destiny. Thank you so much.
Perfect timing. Thank you so very much. That was a wonderful presentation. I would like to see if Team Genesis is in the room. Anyone from Team Genesis, please let me know.
Hi, ma'am. Team Genesis is in the room. May we just have 5 minutes? We're just finalizing one paragraph.
Absolutely. You have 4 minutes until your starting time. So feel free to chat. If you have any questions about the previous team, feel free to utilize the chat to answer any questions. And Team Genesis, in 4 minutes, please just go ahead and get started. We will be ready. While we wait for the next team, is anyone from Team Aries X here? Please let me know in the chat if you are here from Team Aries X. You're next after Genesis. Okay, thank you, Andrew. Okay, the clock is running on Team Genesis. Go ahead and get started.
Hi, ma'am.
I'll take these slides, if that's okay.
If you're talking, we can't hear you. Jack, are you talking? You're muted. You've been muted this whole time. You have to start over.
Pardon?
Were you talking, Jack?
No, sorry.
Oh, who's talking? Because I can't hear anything.
Ma'am, I'll be starting on a self count of 3, 2.
Okay.
Good morning, afternoon, or evening, wherever you are in the world. Since 1998, the Mars Society has dreamed of going to Mars. We are Team Genesis, and we believe we have what it takes to accomplish just that. We spent the last month and a half carefully designing a mission to go to Mars. We are here today to shock you and the world into taking action. Ladies and gentlemen, let us go to Mars.
Are there more beings like us? This is a question we have asked ourselves for decades. Our ancestors were fascinated by the moon, and through folk tales and legends, made it come to life with mythological figures. After finding no such life, however, we now turn to planets of our solar system.
Mars is a reachable and promising candidate for signs of or active life. Unlike Venus with melting temperatures, or Mercury, for example, with sun-scorched surfaces, Mars has a magnetic field and an atmosphere similar to Earth's. With scientists suspecting microbes could be alive in subsurface aquifers, life on Mars is unlikely but not impossible.
With each uncrewed mission to Mars, we have grown more and more intrigued with the possibility of life on the red planet. What was first thought to be a barren wasteland was discovered to resemble Earth in its past. Despite this, there are many things we still do not know about Mars, and Team Genesis believes we have reached the limits of what probes can achieve.
By sending humans to Mars, we can conduct a wider range of experiments, as well as being able to flexibly alter our mission goals and improvise. In addition, fledgling technologies may be further developed through utilization of them in the mission. But ideas don't fast to space, plans do. And so, we bring to you the Genesis program, a visionary concept for a crewed mission to Mars.
The Genesis mission will be a groundbreaking endeavor to land humans on another planet. As it is the first of its kind, it must set a precedent for interplanetary travel and humanity's expansion towards the solar system. Therefore, the Genesis mission will have multiple space agencies in cooperation, transcending borders and regional disputes.
NASA, ISRO, ESA, and the CNSA lead the project, each granted an astronaut of their own nationality on the Genesis crew. These agencies were chosen for their proven expertise in spaceflight. NASA was the first agency to land humans on another celestial body, and ESA has revolutionized stellar mapping with the James Webb and Hubble telescope and has achieved the most distant landing from Earth with Huygens.
ISRO has demonstrated excellent efficiency and cost-effective innovation, reaching Mars on its first attempt with a record low budget. In addition to having designed reusable rocket systems, CNSA brings expertise in space-based construction, which is the main pillar of the Genesis program. Combined, these agencies pool together resources, innovations, and experience to represent humanity's collective efforts to reach the red planet.
JAXA and the CSA will also collaborate on the project, albeit without astronauts of their own. Seeking their help would mean reducing the financial burden and potentially lead to more innovations, thus proving JAXA and CSA as great assets. In return for their assistance in the Genesis mission, they will be guaranteed support for their own missions in the future.
A crew of 4 astronauts will be stationed on the surface of Mars for 1.5 years, living inside of an inflatable incubator with life support and a greenhouse. Their main aim is to find irrefutable evidence of life on Mars through a variety of means. The mission goals will be further elaborated on the coming slides.
Genesis mission will use a human transfer to get to Mars, through a window for the most efficient trajectory that opens up once every 26 months. The first window will be used to land the reactor responsible for power generation, and another to land the mission gear and astronauts. Our main objectives are: 1. Life detection. The Genesis missions will attempt to definitively conclude if life on Mars existed at any point in time. While previous Mars missions have found potential biosignatures, they remain unconfirmed. For example, the Perseverance rover found a rock named Cheava Falls, containing features that could have been formed by microbial gravity activity. However, abiotic processes could also have created them. These uncertainties exist due to the narrow range of equipment these probes are fitted with. In other words, probes are limited by their design. Humans, on the other hand, can adapt to situations and react to unexpected discoveries. To aid the astronauts in their research, the Genesis mission will equip them with a wide range of equipment and ensure they can be used in a variety of circumstances. While it is the scientific consensus that the existence of metazoan life that is composed of multiple cells forming tissues and organs, is impossible on Mars, this is due to the scarcity of oxygen in our decent atmosphere. These are all variables that metazoan life requires to fuel its cells. However, microbes require much less resources, with some extremophiles being able to survive lethal doses of radiation in vacuum. One such microbe is D. radiodurans, which has been theorized to live for hundreds of millions of years buried under Martian soil. Hence, scientists theorize that microbial life on Mars, if any, would be present buried deep underground, hiding in caves or preserved in ancient permafrost. As such, the Genesis mission will explore lava tubes, sample soil, and ice to find remains of or active life.
A key problem with long-term stays on Mars is food. It is heavy to be transported from Earth, and so growing crops on Martian soil would save resources, as plants would have been proven to grow on it. The Genesis mission will cultivate crops as a source of nutrients and vitamins, namely potatoes, lettuce, kale, tomatoes, and beans. Martian soil will be brought from the outdoors, then heated and immersed in water to break down and dissolve perchlorates, a toxic salt present in the regolith. After, it will be given fertilizers and given seeds. Human feces will be thermophilically composted, a process using bacteria active at high temperatures to break down biomass and put into the soil as organic matter.
Carrots are a good source of vitamins and fiber, notably improving digestive well-being. Potatoes will be mainly cultivated for their antioxidant properties and the density of carbohydrates. Not only that, in the case of certain botanists of the crew get stranded on Mars, they can live off of them. Johan, please take the stage.
Martian soil will be brought from the outdoors, then heated and immersed in water to break down and dissolve perchlorates, a toxic salt present in the regolith. Afterwards, it will be given fertilizers and given seeds. Human feces will thermophilically be composted, a process using bacteria active at high temperatures to break down biomass and put into the soil as organic matter.
Carrots are a good source of vitamins and fiber, notably improving digestive well-being. Potatoes will be cultivated mainly for their antioxidant properties and density of carbohydrates.
Lettuce can help with fast wound healing and organ function. Tomatoes are known for their tart sweetness, and so they can help with crew morale while still being a vitamin-packed plant. Kale is a nutritionally dense food, notably containing calcium, which helps maintain bone structure.
Lettuce can help with fast wound healing and organ function. Tomatoes are known for their tart sweetness, and so they can help with crew morale while still being vitamin-packed plant. Kale is nutritionally dense, notably containing calcium, which helps maintain bone structure. Alfalfa, named after the organic Arabic phrase of father of all foods, is a superfood rich in phytochemicals, minerals, and vitamins, while also fixing nitrogen in the soil. That is also done by green peas, which can serve as a source of plant-based protein.
The Genesis mission will aim to bring back a variety of samples from different sites of interest on Mars. These samples will be from different terrain types, have different mineral compositions, and potential biosignatures. The Genesis mission will collect and bring back four main types of samples. One, sedimentary and metamorphic rocks found near the mission site. Two, ice and permafrost cores. Three, Martian regolith and greenhouse soil. And fourth, rocks containing potential biosignatures. Sedimentary and metamorphic rocks will be brought back because they can tell us more about how geologic processes shaped Mars, the same going for Martian regolith. In addition, permafrost cores can shed light on the ancient climate of the red planet, with the potential to contain microbes. Samples of the habitat's greenhouse soil will show how microbes and organic matter interacted with Martian regolith, providing an analog for how microbes of Mars may have evolved in their native soil. Finally, rocks containing potential biosignatures can be further analyzed on Earth if no definitive proof or life had been found during the mission.
Most Martian caves formed during the Noachian or Hesperian periods of Mars, geologic epochs that were volcanically active and likely habitable. If any microbes were alive back then, they could have survived in Martian lava tubes or been preserved there. To explore them, the Genesis will launch two capsules in one rocket. Partway through their flight to Mars, the capsules will separate and adjust their trajectories. The capsule containing the main mission equipment and the crew will head for the landing site, whereas the other, containing two probes called CECE and Caldera, will lead to the Arcia Mons region to explore Martian caves. Caldera serves as a relay point and analysis hub, whereas CECE is a small spider-like crawler that will explore the caves up close.
CC will be fitted with a sample collection drill, flashlight, microscope, stereo camera, then OPTR system to analyze cavern walls for biosignatures. It'll look for areas of interest, analyze it with OPTIR, then sample it, and then examine it under an onboard microscope before selecting it for return to Caldera. Environmental sensors will also assess internal conditions and habitability. After gathering samples, CC will return to the surface by retracing its steps into radio range, where it'll transmit photos to Caldera and return samples to it via a sealed transfer port. CC uses legs instead of wheels as it is more reliable on uneven cavern terrain. Caldera will map the Martian underground with a sonar and relay instructions from human operators to CC. It communicates with Earth and the Genesis space through satellites, such as Maven, Mars Express, with a Tianwen-1 orbiter. At the same time, it analyzes samples provided by CC using spectrometers, an electron microscope, XRF, and XRD tools to ensure thorough and accurate results. Powered by an MMRTG, it'll be able to reliably function in any weather for extended periods of time. The Genesis mission gear will be landed on G-Trinalis Mensae, region north of Arabia Terra. Located in the dichotomy boundary of lowlands and highlands, the region supports meson-like landforms shaped by glaciers. Its positioning makes ancient cratered highlands and the lower lowlands accessible, as well as sedimentary and metamorphic rocks formed by aeolian erosion and pressure. As there is evidence of ice just below the surface, permafrost can be sampled and analyzed for climatological data, as well as to search for life. Satellite imagery shows mechanical breakdown of rocks by wind occurred in this region, depositing sediments which turned into sedimentary rock over time. In addition, while Mars had no tectonic plates, the bombardment of meteorites on the highlands could have formed metamorphic rock, as well as it being present between the dichotomy boundary due to constant stress and pressure.
Habitat design. While a 3D printed habitat built from bricks composed of Martian regolith is possible and would demonstrate ice area, it is impractical as the Genesis habitat comprises a few modules and is shielded from any sharp objects by the two reflectors positioned to its left and right. In conclusion, 3D printing technology would likely be utilized by future settlers needing to build complex lunar structures, but is unfit for a simple, minimalist, and quick to set up habitat such as the one the Genesis habitat requires. Time spent processing Martian regolith, slowly 3D printing breaks increases initial time spent on the Martian surface, and the non-renewable life support resources like water and oxygen. Whereas the Genesis habitat can get recyclable and closed-loop life support up and running in just a few hours or less. So for our habitat, the modules are placed on the ground and regolith is placed on top. Then the module is inflated. The protection from micrometeorites, debris, and radiation will be ensured by the regolith on top of the habitat and the mirrors placed on the side. These mirrors also reflect visible light in the habitat. Photovoltaic panels will also be placed on top of the habitat to support the nuclear power. In time, the pressure inside will get to 500 millibars. The average temperature will be 20 degrees Celsius, and the air composition will be 35% oxygen, 64% nitrogen, and 1% other gases. The habitat includes research stations, personal offices, storage, a greenhouse, and bedrooms. The greenhouse will serve as a test bed for cultivating plants directly in Martian regolith, exploring which crops could support future human settlements. One of the problems with an inflatable habitat is material stress, namely in areas near the airlock. Repeated pressurization and depressurization will cause microtears to form in the habitat fabric. This has the potential to rip the structure apart entirely during an airlock cycle, causing explosive decompression. To prevent this, the airlock will be a separate component from the habitat canvas altogether, glued to the inflated habitat modules with resin as opposed to one end of the airlock being habitat canvas and the other being solid. This ensures the inflatable structure of the base is not undergoing a stress/distress cycle, which will be all contained within the airlock.
The Genesis mission will produce water through the Sebaceous process, which facilitates the exchange of elements between hydrogen and carbon dioxide, resulting in water and methane gas. The hydrogen will be transported to the mission site in tanks, where they'll be connected to the reactor. Only a small quantity of CO2 will be needed to kickstart the cycle, as the reactor will continuously convert exhaled carbon dioxide and oxygen into water, some of which can be electrolyzed into oxygen. A system like this in real life aboard the ISS and is called the CRA, Carbon Dioxide Reduction Assembly, with each unit producing 2.4 kilograms of water per day. The Genesis mission will bring on board 472 kilograms of hydrogen, enough to yield 10 liters of drinkable and reclaimable water, the rest going towards continuous O2 production.
Solar panels, while effective in powering short-term missions, have been proven unreliable in the long run due to dust buildup. While this can be remedied with astronauts cleaning the panels daily, their output is insignificant in the scale of power that the Genesis habitat requires, amounting to around 1 megawatt hours per sol. This would equate to around 450 square meters of panels, which is widely impractical. As such, the Genesis mission will soft land components of a BWXT Pele microreactor 2 years before the main mission equipment launches.
We will use 3 surface vehicles, a transport rover, an uncrewed helicopter, and an excavator. The Genesis mission's transport rover will be based on NASA's Lunar Terrain Vehicle Perseverance, built to cross all types of terrain on Mars. It features wheel suspension, systems to allow it to cross over large rocks, as well as a rounded design to put less stress on the pressure seals. In addition, a radio allows the controller to communicate with the habitat and crew. A small computer in the cockpit can calculate driving distances and time based on satellite data, as well as the local weather. Fitted with an 18 kilowatt per hour rechargeable battery, it can travel around 90 kilometers on even terrain with a full charge at a top speed of 25 kilometers per hour. The sample collection and exploration helicopter, it's in the next page, or SCE for short, is based on NASA's Ingenuity. However, it directly addresses the issues encountered with Ingenuity. The landing struts will be more shock absorbent, the wings more durable, and instead of indirect navigation, the SE will use satellite imagery to determine its location, and only fly when said satellites are within transmission range. In addition, the servo motors will be hermetically sealed to prevent dust from blocking them.
Safety systems. The safety systems consist of the mission gear being made of metal, synthetic metal, or flame retardants to prevent fire. There will be two subatomic reactors, with one producing more water than the crew needs, and the excess water is stored to be converted into oxygen later. Hot swappable equipment such as filters, fans, or sensors. There will be sensors for smoke, pressure, temperature, and air consistency in every room, and alarms will sound in case measurements aren't in the acceptable window. Routine inspections will take place every second day for life support systems and safety equipments, and every month for all systems. These inspections are meant to address any wear and tear and to make sure that every system is running properly.
To go to Mars, we are going to need courageous, brave explorers, the Columbuses of space, to carry out these tasks and discover a new world. We will select and train our astronauts via the following requirements.
Every astronaut must have a STEM advanced degree in agrobiology and engineering. They also must spend at least 3 years living in Mars-like desert environments, which will be funded by the joint Mars.
Of course, they must also undergo training sessions with the NASA Xemu spacesuit, which is going to be used on Mars. And each one of them must have basic first aid medical training.
They will also have specialized training for each of their roles in the mission. What are those roles, you may ask?
Our leader, the first astronaut, must be strategic, cool-minded, calm under pressure, adaptable, courageous, and willing to do anything for the mission.
Their role, an agrobiologist with expertise in desert conditions, perfect for growing crops on Mars. He must also be a cave explorer with knowledge of subterranean habitats.
Our second astronaut must be a biologist with knowledge of life detection protocol and equipment. They will be essential for one of Mission Genesis' primary goals, life detection on Mars.
Team,
The third,
excuse me, pardon the interruption. You're over your 20 minutes. Just to be fair to everyone, how many more slides do you have?
Ma'am, I think we have 4 more short slides, ma'am.
around 5 more slides.
Okay, well, it's not fair to the other teams to give you extra time. You've been speaking for over.
It'll only take around 2 to 4 minutes, ma'am.
Okay, so I will have to say, I'll give you 30 seconds to finish up to be fair to the other teams, okay? So go as quickly as you can. They will still get a copy of your full report.
Right, ma'am. The third astronaut should be an engineer, essential for the setup and operation of the habitat, drones, rover, etc. They are also an essential member of the crew in case anything goes wrong with the above technologies.
And finally, our last astronaut must be an experienced pilot who is good at adapting to high-pressure situations. As a psychiatrist, they must conduct regular health checkups on the crew. She must also have advanced medical training in case of emergencies.
For the spacesuit, we have chosen the NASA Xemu spacesuit, and the food requirements for a mission to Mars are as follows. Each astronaut needs 2.39 kgs of food daily, which provides approximately 3,000 calories. So, in total, for 4 astronauts in 1.5 years, this is approximately 5.5 tons or 5,033 kilograms of food.
Thank you so much, team. You are out of time. You will still be able to provide your full report for other teams to review. Unfortunately, the next team, Team Aries X, is unable to present. So our next presentation will be at 8:55 a.m. Pacific time. So that will be 11:55 Eastern time. So we have quite a long break. So I'm going to stop the recording. And the next team that presents will be Team Phoenix. Is anyone here from Team Phoenix?
All right, welcome everyone to Team Phoenix's mission in the International Mission to Mars Design Challenge. So our mission will last around 1.5 years. Everything will go in one launch. We will have 4 astronauts as our crew, and our total weight will be 29 out of the 30 metric tons. So our landing site will be at these coordinates, and it'll be close to this place called Elysium Mons, which is a great place for our potential studies. It sits on a large subterranean ice plain, which is a great source of drilling for water ice. And this crater here is great for natural radiation protection and dust storm protection. And you can see here the landing site relative to the center of Elysium Mons. Now on to engineering.
So the first thing we'll be going over here is the habitat, and here's kind of just like a little drawing of it. So first, next slide, please. Can you move this? Yeah, thank you. One slide before. Thank you. Okay. So this is kind of like the base map of our whole base. We have the habitat, which will house the crew's sleeping area, life support. A little bit close next to that will be the rover storage for both of our rovers. And also close by is our solar panel area to get solar power from that. And around 1 kilometer away, we will have our reactors. And next slide. This is the floor plan for our habitat. So we have a lab, the storage area, a common area plus the bathroom, a sleeping area which is connected to that, and a section of just essential equipment and a medical bay. In total, the whole habitat section here covers around 1,020 square feet. And just to note, these lines don't actually represent walls, they're just kind of general areas of where things would be. Next slide. So just as a kind of what exactly the habitat's made of here. So we have a couple layers. Our first outer layer is the actual inflatable Vectran. And we chose Vectran because it's light and it's really strong and can handle the kind of environment that Mars will push the whole habitat through. And then on the inside of that, we have a polyethylene layer. And then we chose polyethylene because aside from the fact that it's strong, it also provides very good shielding against space radiation. And then towards the inside of that, there'll be 4 aluminum poles. Now, what these do is this supports the roof of the habitat, so that in case there's any sort of depressurization, the roof just won't collapse on anyone inside. Additionally, we do have infrared heaters, and these provide heat, especially in the Mars nighttime, which gets really cold. We also cover the floor with vinyl, and we chose vinyl because it's weather resistant and highly temperature resistant. Okay, next slide, please. And for our lab area, this is where we'll be running most of our experiments. We'll have rotary kilns, rock crushers, with a total area of around 200 square feet. There's also a greenhouse here. We didn't put a picture of that, but there will be a greenhouse that we'll explain later. Next slide. And then for the essential equipment area, the biggest thing is the ECLSS. And what this does is this puts oxygen back into the air. It also recycles most of your water and also provides temperature control. Additionally, we will have the medical bed. This covers around 81 square feet. Next slide. Okay, now this is a sleeping area. It's separated from the actual habitat a little bit, just to give a little bit more space and also make room for the common area. And we'll be using 2 bunk beds, all of which fit within our sleeping area here. The bathroom is additionally, it's around 4 by 4 feet, and it uses a vacuum suction system to discard waste. Your liquid waste goes to the ECLSS to actually be reused and turned back into drinkable water, and the solid waste is put into resealable bags, which can be used for experiments and other purposes as well. Next slide. As for our storage system, we have 140 square feet of storage, and it'll be mostly utilizing these shelves. This is kind of just like the room layout, so you'll just have shelves kind of put right next to each other. And this will also house all the food necessities and spare parts for the rover, tools, and other stuff like that. Next slide. Then outside the habitat, we have our rover storage. Now this is sort of like how to say, a rectangular prism shape. It's 10 by 16 feet, allows for the storage of our rovers. It's built on the same kind of wall siding that we use for the habitat. That way, the components inside can stay heated and it doesn't get way too cold or too hot. Additionally, we do have a radio antenna at the bottom. This allows us to communicate with the autonomous rover that we have. And on top, we also have a transparent moon window. And what this does is it allows us to charge the rovers via solar panels. And then we'll move on to the vehicles.
All right, so we have two vehicles here. We have an uncrewed vehicle and a crewed vehicle. So we'll start off with the uncrewed. It'll be a rover similar to the NASA CREX-2, which already exists, and these rovers can autonomously drill and sample various types of materials using this Trident drill, which it'll collect material in, and then it'll sample them through these funnels and the instrument bay. And so the rover is supposed to function like a scouting role. So the crew sends it out to a location that it seems is promising. The rover will go there, get a few samples, come back, and then the crew will judge whether this is worth sending a crewed rover to extract material. And its compact size and proven use already make it an ideal autonomous rover to be used by the crew. It runs on a 4 kilowatt-hour battery pack and it has a top speed of approximately 6 miles per hour. Next slide. And now we go to the crewed rover. So this can fit up to 2 crew with a volume of 16 cubic meters. It has an outer shell made of aluminum alloy like lithium aluminum. It has an aerogel insulation with carbon fiber interior panels. Its windows are made of fused silica glass with radiation shielding protection. It has a titanium and alloy wheel frame with a nitinol, which is nickel titanium, and that type of mesh is what creates the tires. Its drill has a titanium base joint with a high-speed steel head, and the drill will be on a gimbal system so that it can reach areas that the rover can't necessarily maneuver in. And it has LiDAR sensors and a camera that can be used for awareness and detection. The rover is powered by a few 10 kilowatt-hour batteries, has a final weight of 3 to 3.6 metric tons with a max speed of 7 to 9 miles per hour. And it's split into a pressurized section which houses the crew and the unpressurized cargo section. Next slide. Okay, so now the storage compartments will have a folding modular design that's held up by an aluminum metal frame surrounded by a foil material to shield from any dust or sunlight exposure. And one additional module can be attached as well. If you see here, you can see 4 rectangles, and that's with the additional module. You can see the aluminum frame, and if you look on the right side, you can see how it folds up, revealing the cargo inside, which is made to give easier access to the cargo and make the rover lighter overall in general. All right, now we're moving on to the power.
So our first main source of power is solar. And what we've designed is sort of like an accordion style folding system for the panels. And we chose to do this because what it does is it allows us to compact the solar panels together, making it super easy for transport and for construction. And we also chose this kind of design because what it does is it allows us that no matter where the sun moves along the sky, it'll always be hitting the solar panels. We'll always be getting electricity as long as there's no like dust storms or something that blocks the sun. Additionally, these panels will have fans on the side to blow air in order to clean them off, along with the crew cleaning them off if necessary. In total, there'll be 88 solar panels, creating a total of around 88 kilowatt hours of electricity. And they will be placed in an 11 by 8 grid, which spans an approximately a 60.5 by 24 foot area. And next slide.
Now our backup power will be nuclear, and in the event that solar power doesn't work, such as like a dust storm or something, then the nuclear power will be utilized to power the life support systems that are still needed to keep the base running. We'll have 4 of these 10 kilowatt kilopower units utilizing Stirling engines that are connected to the habitat with the 1 kilometer insulated copper lead wire. This will translate about 160 volts with 246 amps to the habitat. It'll be located a kilometer away from the habitat to ensure that the crew is safe and it minimizes any contamination risks. This reactor has been tested by the NASA Fission Service Power Project, which aims to provide a reliable power source to human outposts on the Moon and Mars. So this reactor has been tried and tested for this kind of mission in mind. and any risks of overheating and a meltdown are drastically reduced because the reactor is located in a colder environment. So if the reactor begins to start heating up, it'll be cooled by the outside environment. Next slide. Now we go into the weight.
So totally our weight here, our flooring is 1,200, and all these are in kilograms. Our siding for polyethylene is 1,890. Aluminum doors for our airlocks are 130. Infrared heating panels around 60. The ECLSS is 3,600. This does include the water supply necessary to create oxygen throughout the time. The Vectran inflatable itself is 390. The radio antenna is 100 kilograms. Aluminum supports in total are 2,169. The bathroom is 250. 30 kilograms of shelving. Around 71 kilograms is the medical bed. 150 for the bunk beds. 10 kilograms of aluminum pipes. 2 treadmills. Next slide. So 150 kilograms of spare parts. LED lights are 10 kilograms. The greenhouse is approximately 6 kilograms. The resistance bands are 3. Our solar panels weigh around 1,600. Our lab equipment is 1,025. The crewed rover is 3,600 kilograms. The autonomous rover is 1,100. We have 4,100 kilograms of food. Our 4 reactors are 6,000 kilograms. The water, 1,500 kilograms, and 30.5 kilograms of lead wire. In total, this comes down to 29,324 kilograms, or 29.324 metric tons. And we'll move on to science now.
Our main goal for the science section was to use Mars's natural materials to its fullest potential. One of these many natural resources would be Martian soil, which is primarily containing minerals like iron, magnesium, aluminum, and silicon. However, it lacks nitrogen, which is a key component of chlorophyll, and this issue of lack of chlorophyll leads to reduced photosynthesis efficiency and ultimately stunts growth. It also lacks organic matter, water retention properties, and microbial life, all key components of plant health. But the big factor here is the high concentration of perchlorates. About 0.5 to 1% pose major challenges. Next slide. So how do we fix all of these issues with the Martian regolith? There's many fixes for the nutrition, which can simply be composting using human waste or food scraps. There's also a more advanced composting called vermicompost, which is enriched with earthworms, and when combined with microbes, greatly improves plant survival in harsher conditions. And then there's also biofertilizer, which is just organic fertilizer that infuses the soil with microorganisms that can balance pH, release minerals. But the big factor that we have to fix here is the chlorite. So one of the simplest methods for removing perchlorate is washing, which is just repeatedly flushing water through the soil, and it can help dissolve perchlorates. However, this does need a lot of water, which is a big, not a big resource on Mars. One good technique is thermal treatment, which when perchlorate reach 400 to 500 degrees Celsius, it actually is able to break down into oxygen and chloride. And in Martian soil, with its heavy iron, this actually doesn't need to be 400 to 500. It can be about 100 degrees less, about 300 to 400 degrees Celsius in Martian soil. However, on this mission, we don't have any equipment that can reach that high, but this is something that doesn't need to be tested on Mars. It can really be tested anywhere with any sample. And the lastly is a recent method. It's a perchlorate reducing bacteria that NASA has been experimenting a lot, and it basically can convert perchlorates into chloride, which chloride is perfectly harmless in small amounts, kind of like salt. You can eat it in small amounts perfectly fine. Next slide. So how do we use this soil to eventually grow plants and a food source for our crew? Well, prior studies did look into that, looking into biomass, germination, and all sides of stuff, comparing lunar, Martian, and Earth regolith. And shocking results were that Mars actually performed better than Earth in most instances. This is mainly due to the study using riverine soil on Earth, which is a not entirely great soil. It's not one you would normally grow plants in, but the fact that Martian soil is able to even do this in the first place and keep up to even a poor quality soil on Earth is very beneficial. One note was that it did lack the water retention, as mentioned earlier, as even being sprayed twice a day, it did dry out a lot compared to Earth soil. Next slide. So how can we improve this even further? A big thing is intercropping, and this is an ancient agriculture method that's been used forever, where you basically plant two plants next to each other that can benefit each other. So say one plant helps fix nitrogen and the other is fast growing. If you plant those together, the one that is helping that nitrogen composition in the soil can make those fast growing leaves characteristics even better. And recent studies that have explored this in Martian regolith were able to yield about 0.5 kilogram of produce, and that is with minimal added nutrients. I believe it was just a little bit of nitrogen. The key component here is that all that intercropping is plants. So all you need to bring is the plants, no extra material. Next slide. And here's the greenhouse setup. It's a simple tabletop setup that just has everything needed, like a sprinkler system, humidity and temperature system, and artificial lights. It's not a full greenhouse that would be outside. It's simply tabletop for testing only. Next slide. That's it.
All right, thank you. That was great. Next thing we're going to be looking at is natural resource utilization on Mars. As we know, in-situ resource utilization is going to be a necessary thing to save a lot of weight when traveling to Mars, and it'll be incredibly important for future colonization efforts. So as we've looked into our study, we found many methods of utilizing Mars resources to create heavy materials that could not be brought back from Earth due to weight concerns. As you can see here, such things include cement, cast metal structures, and propellant along with liquid water. The first thing we're going to be looking at is concrete. As we know, that's an essential part of Earth's infrastructure, and we believe it can prove useful again in Mars, giving foundational support, rigid structures that will be essential for a colony. They also provide moderate radiation protection on their own. As you can see on the right, a lot of the materials found in Martian soil match with a kind of cement found on Earth known as Portland cement. Other materials that occur on Earth are gypsum, liquid water in the form of ice that can be melted, and aggregate rocks, which can just be any kind of general rock that you find on the surface. This little graph here is going to kind of goes over the process that I've discussed. It begins with processing soil samples in a rock crusher, refining them in a ball mill, putting that material in a rotary kiln at around 1500 degrees Celsius to convert that material to a substance called clinker, cooling that clinker and combining gypsum in the ball mill again to produce a dry cement mixture. Combining that cement mixture with an aggregate and water will produce Martian concrete. This is a success. This material could be employed at a larger scale by future colonists to construct structures, foundations, build a colony on Mars. The other thing I'm going to be looking at is metal extraction. Now we know that most of Mars is covered in oxidized metals, which is what gives us its signature red color, specifically iron oxide right there in the middle, FeO. In some other places on Mars, there's a substance known as hematite or Fe2O3, which is better for the electrolysis process that we're going to be employing on the surface. Also, Al2O3 or aluminum oxide is another substance that we're looking into due to its lightweight and abundance in the Martian soil. So, as I mentioned, electrolysis technology can separate iron oxides into their pure metallic form, and utilizing a lab-grade furnace, which can reach about 200 degrees Celsius, converting this pure iron into molten iron, and then pouring it into cast, which could be designed to test possible differences in metal casting in a low-gravity environment. And as with the concrete, if these experiments are a success, they can be employed by the future colonists to construct strong, rigid structures without having to bring the materials from Earth. As is already proven to work, we're going to be looking at fluid repurposing, specifically electrolyzing water and producing rocket fuel from that. So as you can see here on the graph on the right, taking liquid water, electrolyzing it, converts it into hydrogen gas and oxygen gas. Cooled oxygen gas in the form of liquid oxygen can be used as rocket fuel. And gaseous oxygen is breathable. Combining hydrogen gas with carbon dioxide and a nickel catalyst, also known as a Sabatier reaction, produces more liquid water, which can be drinkable or brought back into the electrolysis process. And methane gas, or CH4, which is another rocket fuel. This technique will also be essential for future colonists who cannot afford to bring enough fuel for a return trip to Earth and need to produce it on the surface. This is more of a future possibility than one for our crew, but Mars has two moons, Phobos and Deimos, which are classified as D-type and C-type asteroids. Phobos is only 6,000 kilometers from Mars' surface, which is incredibly close. It's the closest moon to any planet in our solar system. and is also both asteroids are rich in carbon, and Phobos especially has a high iron content, meaning that due to the lower gravity on Mars and the distance between the planet and the moons, this could potentially pose the first recorded instance of space mining for future colonists.
Hi, sorry to interrupt, but your time is about up. And to be fair to all other teams, please wrap it up in the next 30 seconds.
Okay, we got 5 minutes, but I can condense it. So please skip to slide 37. Okay, basically, this is our crew. Engineer is the captain. The other 3 scientists are there to help. Next slide. Captain is in charge. He's going to just solve most disputes unless ground controls needed. Next slide. We're bringing 4.1 metric tons of food. Why? Because even though we don't need it, we want to have a backup clutch in case some kind of food is spoiled. Next slide, please. We need to make sure the astronauts are fit in space. So this is why we're going to have exercise materials and resistance bands to keep them safe so that they can return home and not get weak. Next slide. We have spacesuits which have protective and utility. Next slide. There are cooling layers, radiation layers, and insulation layers, and a bladder layer, but we don't have time to go over those. Next slide. And lastly, there are just some other key functions, which I also don't have time to go over. So last slide. Thank you very much. Any questions, you can feel free to ask later. Thank you.
Please put questions in the chat. And is Team Project Ascend here? I have emailed you. It's interesting that people aren't coming who were actively participating in the other portion. Okay, Team Project Ascend, your clock starts in 3 minutes. Everyone take a stretch break while we wait to see if they arrive. Yes, they are. Project Ascend is going to be arriving. So stand by for their project.
Hello, can you hear me?
Yes, go right ahead and begin.
Okay, hello everyone. We are Project Tartarus, and basically we're a part of Team Ascent. My name is Bing. We have Steven, Abigail, Katie, Lisa, and Ethan within this team. So here's going to be our mission overview. The location is going to be Arabia Terra. The time span is going to be 1.5 years, so we'll hit the maximum on that. We'll have 4 crew members, and here are our 3 main science objectives. First, we need to gather data on climate and geological history so that an informed conclusion can be made about the habitability of Mars and help guide future missions. 2, find a reliable water/ice source for potential civilizations in terraforming. 3, establish a long-term greenhouse system capable of producing fresh vegetables and fruits to support potential sediments in future missions.
So more specifics on the base location, which is in the Arabia Terra region. The base will be situated in the Cotito crater, because the further study on the location can find exposed cave entrances, which we will talk about later about the more specifics on the base on where the base will be situated inside the crater. The surrounding area has relatively low elevation as it transitions from the southern highlands near more geologically higher areas to the northern low-lying plains. In the surrounding area, there is also subsurface ice with the close proximity to the base, allowing easy ice and water extraction with a depth of around 0.7 meters or deeper. It has a slow slope, allowing it's a great candidate for also geological studies, and then the elevation varies from the craters to a more flatter surface, and then those are the location coordinates.
Each astronaut will have 2 main specialties. The first one is commander and technician. They will oversee the mission execution and make decisions during emergencies, control rovers and UAVs, and maintain contact with mission control. Engineering/electrical specialists will repair any damages to the base, especially after disasters, monitor signal and power, as well as life support system. Biology/medical specialists will spend a lot of their time conducting experiments and maintaining the greenhouses of plants and bioreactors. The geologist/chemist will analyze terrain and understand the climate history of Mars, as well as conducting experiments and working alongside the biologists.
Okay, so here's going to be the base layout. So the base is going to be located inside a Martian lava tube. We'll talk about more of how we set up inside there. And within that, we have small nuclear reactors to power all operations offsite. So they're going to be around 500 meters from the habitat to ensure safe distance. So the main habitat is going to store majority, if not all, of everything that is needed for the mission. It's going to store life support, crew quarters, its laboratory, storage, airlock systems, communications and control, and basically any pressurized vessel. So we can see in this diagram here, we have the main thing within this lava tube, and basically to the left is the nuclear reactors, and to the right is going to be eventually the tunnel entrance. So here's going to be our habitat layout. So going back to the previous slide, we can see that this blue circle here's going to be our habitat. So first we have our laboratory and medical center, which is up here. This is going to store specialized equipment for scientific studies and first aid and critical life support just in case someone gets injured. Next, we have the sleeping quarters and lavatory, which is going to be down here. It's going to store the beds, the private space for crew members, and storage for their private belongings. And finally, it's going to store their bathroom as well. And then we have our airlock, which is going to be our first rigid module. It's going to store tools, and suits. Then we have our greenhouse and biostorage. This is going to store, of course, the greenhouse, and it's also going to store storage for food and microorganisms. The reason why we have this allocated is because all of our life forms on there, except the humans, of course, are going to be isolated within this one containment, which makes it really easier to confine and monitor just to make sure that no Earth organisms escape onto the Martian surface. And then finally, we have our control room and storage. So all communication from Earth and on Mars are going to be monitored within this control room, and also sensors placed throughout the rover, the UAV, the nuclear reactors, and the habitat in general are going to be monitored here as well. Also within this inflatable is going to be non-biological storage. And finally, in the middle, we have dining and entertainment. So we're not going to have a full-on kitchen, but there's going to be a table for them to eat at. There's also going to be a pretty large skylight window so they can see into the cave they're living in. And also there's going to be board games, television, etc. So let's move on to our rigid module. So this is the main module and airlock, which we can see here. So the walls are going to be multi-layered. The very inside layer, the ones that the courier interacts with, is going to be plastic laminate panels. These are antimicrobial, visually appealing, and most importantly, they're fire resistant. The second is going to be an aluminum layer. It's going to be mostly a pressure liner, and it's going to be the main structural bearing material for the entire habitat. Third, we have our polyethylene liner. This is going to be our first layer of thermal insulation. And fourth is going to be our aerogel tile layer. It's going to be like hexagonal tiles. It's going to provide thermal insulation. So the reason why we have this many thermal layers is because within the Martian lava tube, you get zero heat from or energy from the sun, and you're stuck within a cave. So it's going to be very, very cold down there. That's why we need all this insulation as well. And the reason why our aerogel is a tile layer and instead of a flat layer is because aerogel is inherently brittle, so that can cause a lot of cracking and stuff due to thermal stresses. So we decided to go for like a starship heat tile design where we can have them be hexagonal and they can expand and contract due to the thermal stresses. And then finally, we have our Kevlar fabric layer, which is puncture proof and helps protect the brittle aerogel tiles. So now we have an inflatable module. It's going to be around the same, a bit different in terms of material from the rigid modules. So the four inflatable modules are going to be connected to the main modules. The first layer is going to be Tedlar. This is again a crew interface layer. It's fireproof, durable, and antimicrobial. The second layer is going to be polyurethane. So it's going to be like kind of a plastic bag texture, and it's airtight and flexible to pressure changers. And our third layer is going to be Kevlar, and it's going to prevent the polyurethane layer from expanding too much. So we call that our structural pressure layer. Our fourth layer is going to be an aerogel infused fabric. This is going to again provide our insulation. And our fifth layer is going to be Kevlar to protect against falling rocks, punctures, etc. So now we're going to talk about the base setup procedure. So first, our UAV, which we're going to use for science experiments, will be set up as soon as we land on the starships and scan for suitable lava tube entrances. Once we find one, our rover will connect to the main module and basically pull it like a semi truck into the lava tube and set it up there. You can see the main module has wheels as well. And then next, the inflatables and airlocks will be transported via the crane on the rover. And again, the rover will transport everything into the lava tube. And then finally, we'll do all other supplies. And then we'll set up our communication array right outside at the cave entrance and wire everything up to the main habitat from the communication room. So now let's talk about our communication module. So in terms of communication from the ground to the satellites in orbit around Mars, we're going to use high gain directional ultra high frequency antennas for communication between base and the Mars rover. So the reason why we're using ultra high frequencies is because first of all, it's a really high bandwidth, which is good. There's so when we have a UHF, itself is inherently minimal range, but since we're using directional antennas and we're going to be tracking the satellite, we have a lot of power focused on one area, so that gives us good range. And finally, power draw is minimal compared to other systems. So again, this is going to be located at the entrance of the lava tube, or it's going to be located where the lava tube caves in or skylight, and this is going to be wired through a long coaxial cable back to the habitat to the control room. So now we're going to talk about inter-Mars communication. Just briefly summarizing, we're going to use again UHF satellite walkie-talkies. And basically we have a bunch of prevention measures just in case there's some risks involved, so we can protect our tower systems. So now let's talk about life support, specifically the oxygen generation and how we're going to store that. So we're going to use a CO2 electrolyzer to electrolysis from CO2 to get our O2. And the reason why we chose this over other options such as H2O electrolysis is it's the safest option. When it comes to oxygen, you can't recycle oxygen like you do with water, like the ISS. It's a very finite resource, and it basically determines the livelihood of the crew members and the success of the mission. So if we have to use a O2 or water electrolysis, we will need to depend on finding and extracting water. And if there's an extended dust storm, that could jeopardize the mission. So we decided to go with CO2 electrolysis because we can take our CO2 scrubbers in the actual habitat and reuse that again. And also we can take the CO2 straight from the atmosphere, pressurize that, and then put it into our electrolysis and make O2. So our CO2 electrolysis is going to be a scaled up version of NASA's MOXIE, which is a CO2 electrolyzer demonstrated on the Perseverance rover. And based on 4 crew members and calculations of how much oxygen they consume per day, we calculated that it would be 19 times the size of MOXIE for our requirements. So around this is going to get us 4.5 kilograms of O2 per day. It's going to use up 5.7 kilowatts, and it's going to be 0.325 metric tons. So now moving on to water reclamation and storage. We're going to have our urine processor, which recycles the water from urine, and our water processor, which takes the water from the humidity of the atmosphere, from the humidity of inside the habitat, and the water from the urine processor, and it's going to further purify that so it's drinkable. And then we're gonna have a water storage tank, which is outside. But the problem with that is it can freeze, and when it freezes, the ice expands, and then you have a rupture, and that's really bad. So in order to keep it warm, we're gonna have external CO2 loops like around as a liner to help keep it cool, to help keep it warm. I'll go more into that later. But this technology has been demonstrated for like over a decade on the ISS and has a 95% reclamation rate. And the other 5% will be done by ice extraction and purification. So finally, let's move on to temperature control. So most heating will actually come from machinery and humans. Because we have so much insulation, we're not losing that much heat. So we won't really even need any heating at all. If we do, we're gonna have backup electric heaters that provide that heating. As for cooling, we're gonna have a water glycol mixture within the main habitat and air circulation piping to take that heat away. The reason why we use water and glycol is because it's a safe, unpressurized, non-toxic piping. And basically the heat within this water glycol loop will be transported to a pressurized CO2 loop, which then disperses heat through the radiators on the habitat. And also it runs through our water tank, which I mentioned earlier, so it can keep that warm as well. So not only does our cooling system take away and cool the habitat, but it also warms up our water tank, which keeps it liquid form, ready and usable. So now let's talk about nuclear energy. We're going to use 3 of NASA's kilopower reactor. Each of them has around 10 kilowatts of maximum output power. It's a nuclear fission reactor with a Stirling engine. What that means is it's relatively safe and it's very, very simple. So 3 of them would have a combined output power of 30 kilowatts, which is enough to power all our mission operations. And 3 of them combined weigh a total of 4.5 metric tons, rounded up for safety measures.
Okay, I'm just gonna sum up the flatbed payload trucks. Basically, it has there's 3 main components: the robotic arm, which is on the flatbed, and because it's a flatbed truck, we can use it to transport water storage from the ice and water extraction as well. And it's has air suspension as well for to traverse the terrain, and it's a dual motor electric truck with lithium-ion batteries to power it. And to prevent rollover, it has 4 aerial stabilizers that are attached to the chassis. Next slide. Next slide. Sorry. The UAV drone mission. So basically, it's a fixed wing autonomous aircraft with a full blended wing body design for maximum aerodynamic efficiency. It's made out of carbon fiber and it's powered by one brushless DC motor, which is powered by multiple lithium-ion batteries. The propulsion is 4 propellers, which spin at 800 RPM to prevent any type of vibration damage. And there's aluminum spars in the aircraft wing to maintain structural integrity. Next one. Next slide. So there's going to be UAV drone deployment. So now we're going to have a rail-guided catapult system powered by pneumatics, which is compressed. Its air will be compressed carbon dioxide, and it's going to have support legs for structural integrity during takeoff. And for capture, it will hook onto the a hook will deploy from the undercarriage of the aircraft. It will then intercept a wire that has tension from 2 metal beams, just like on the picture on the bottom right. After being caught, all the forward momentum will cease, therefore negating the need for any type of landing gear on the rough terrain. Okay, the UAV drone application, there's going to be 3 UAVs sent to Mars. UAV's one mission is to use LiDAR and also aerial cameras to find subsurface ice. And also, UAV2's mission is to just take any atmospheric data, including a climate sounder instrument, and then it'll also take aircraft turbulence and other stuff. Next slide. So basically, ice water extraction is going to have a Rodriguez well, drilling into the regolith and preventing any human contamination. It's going to have specific procedures when taking out ice samples to prevent basically mixing up the data set. And also after that, it's going to be powered by a solar and battery, so it can allow the well to drill autonomously and during the night as well. And after that, it's going to have water pumped out using a basically melting the ice, and then it's going to be pumped up into a 250-gallon storage tank, which is placed on top of the truck and be sent back to the base for a filtration process. Next slide.
The first experiment that we would do is a long-term one, which will be how Martian conditions have effect on humans. We will test for bone density, muscle mass, radiation exposure, and etc. Another one is that we're going to test regolith to analyze its composition. This information can be used to determine if we can extract nutrients from the soil and use them for plants and humans. And it could also be used for structural materials. Another experiment is to test if microbes, specifically the chloromonas, are able to reduce the amount of perchlorate in regolith that is non-toxic to human and plants. This is crucial during long-term stays in order to create mass-producing farms.
For our climate experiments, our first experiment is over the expedition period, 1.5 years, we're planning to study climate patterns across the Martian surface in 4 distinct locations that we deem critical for human habitation. A couple factors to note are storm frequency, because Mars has a lot of high-intensity storms, those need to be documented in depth. Temperature measurements, pressure measurements, sunlight exposure, which goes in hand with the radiation experiments we're going to do, season changes, natural disasters, soil temperature, all that. And then for experiment 2, we're going to use the factors that we find to determine habitation in these zones and mark out critical climate zones across the Martian landscape.
Okay, so the greenhouse will be separated into a couple sections for the laboratory and the plants. Plants will be based off of large plants, small plants, and medium plants. The crucial ones are greens, potatoes, beans, and tomatoes. We're going to use a staggered planting rotation to prevent any gaps within the food. We will use a hybrid of soil beds and also hydroponics to reduce water usage and also soil volume. And the lab will be separated to prevent contamination.
Sorry to interrupt. How much more do you have because your time is up? How many more slides?
Yeah,
do you
just
have?
like 2 more slides, probably like 30 seconds.
Okay, 30 seconds. There you go.
Okay, so here we have entertainment sanity. Of course, we're gonna have movies. We're gonna have pre-downloaded movies because we don't have a live communication with Earth. We'll have social media. They can't really talk with their family or such, but we'll still have social media so they can doom scroll. So sanity, we have communication down to Earth. Teamwork and collaboration is gonna be really critical. We're also gonna bring exercise equipment. It's gonna be located in the medical bay. They're gonna have a good routine, keep a good routine. Sufficient sleep, proper meals, and sufficient nutrition is really important. That's why we have fresh vegetables and breaks. So here's our final slide. In terms of our mass budget, our rigid habitats, which include our airlock and our main hab, is going to be 3 metric tons. The inflatables, the 4 inflatables are going to be 2 metric tons. The life support and critical systems are going to be 4 metric tons. The storage, including the water tank, batteries, and food, are gonna be all equal to 5 metric tons. The nuclear reactors are gonna be 5 metric tons. The scientific equipments located in the laboratories or on the nodes outside are gonna be 3 metric tons. The rover plus the UAVs are gonna be 3 metric tons. We have 5 metric tons of margin. We have 0.65 metric tons of food. And finally, we have 0.2 metric tons of greenhouse equipment. Thank you. Yeah.
Thank you. Great presentation. Is Team Red Horizon here? I have emailed and I have not heard back from them. Is anyone from Team Red Horizon here? Okay, the clock will start ticking for Red Horizon in 3 minutes. The next team after Red Horizon is the Fantastic Six. Is anyone here from that team already? I'm going to stop the recording in case,
Hi, I'm Elena Flores, and this is Brianna Chavez. Unfortunately, Brianna Chavez was not able to make it with us today. So today I will be explaining our Mars exploration mission we have for our 18th month mission. So our mission, we want to give our astronauts a full concept understanding mission to Mars, including valuable training, engineering, key concepts, dangers, etc. So our astronauts, what are we looking for? For education, we're looking for a master's degree in STEM, science, technology, engineering, math, from accredited establishment. 2 years of professional experience in the related field, or at least 1,000 hours of pilot experience is preferable for experience. Physical and mental preparations. Physical fitness. Must be in good shape to experience physical challenges. Mental activity. Must be able to remain calm under situations and can adapt easily to new environments. Mars environment. So, first we're starting off with volcanoes. Volcanoes occur in the Thracis and Elysium region. Elysium Mons contains the second largest volcano on Mars. The volcano can be 72,000 feet tall. Next, we have dust storms. When winds blow faster than about 20 meters per second, 45 miles per hour, they can pick up dust from the surface, carrying it to great heights in the atmosphere. Martian dust storms occur at local regions and global scales, which can ultimately hurt our Martian crew. Martian craters. Ella's largest craters. Base measures 16,000 x 2,000 kilometers, roughly twice the size of Alaska, located within two volcanic regions on the red planet called Thracis. A crater's size depends on the mass and velocity of the body. Dangerous substances. silica globules, and really can't say these names, but these are contained in the Martian dust, which can ultimately hurt ourselves. And yeah, frontier terrain formed in the experimental and northern latitudes, characterized by extensive smooth and lowland plains. Valves more than 2,000 miles, 3,000 kilometers long, and 370 miles, 600 kilometers wide, and 5 miles, 8 kilometers deep. South of Valles Marinas is a very ancient terrain covered by many impact craters extended from the Nokia's labyrinths. About Mars. Mars' atmosphere is 95% carbon dioxide, 3% nitrogen, 1.56% argon, and it has traces of oxygen, carbon monoxide, water, methane, and other gases. Mars has no atmosphere. Mars is on average 140 million miles from Earth. Reaching Mars generally takes somewhere between 7 to 10 months, flying a relatively direct route. NASA's Mars I can't say that, I'm sorry. Orbiter mission took about 7.5 months to reach Mars. The highlighted orange text is the most important part about our Mars to take into consideration while thinking about Mars. Roles on a Mars team. So first, we're going to start with our engineers. Construction engineers. This is a crucial role when going into space as there needs to be someone on board to set up and maintain a Martian base. Specialized engineers. Specialized engineers are important because the area of expertise they have will benefit the whole ship and crew combined. Then we have our scientists. First, we have geologists. Geologists will be helpful because they will already have past knowledge about Mars and will be able to help in that aspect. Biologists. A biologist's job is to discover new life on Mars and protect the life being brought to Mars. Climatologists. A climatologist can understand the Martian environment like a hazardous space environment, and they can also find water sources. Physicians. This role can be important because they can handle medical emergencies and can provide daily routines, and also help with mental and physical health, which is why they're so important. And then we have emergency medical technicians, EMT. EMT are helpful in a way. If the physician isn't around, they are there to assist until the physician arrives. Then we have generalists. A generalist job has many elements. For example, one is being very reliant, having a very good foundation of their surroundings. There will be many challenges and tasks, and being a good team leader. These are all the roles on a Mars team that we need to make our Martian crew. Without these people, we won't be going anywhere because they all help each other in a way. So first, we're gonna explain our astronaut suits. So first, we're gonna talk about the upper torso. So we have our gloves, helmet, arms. Then we have our life support system, communication system, maximum absorbent garment, MAG, collects urine produced by the astronaut, liquid cooling ventilation garment, LCVG, removes excess body heat produced by the astronaut during spacewalks. Cooling garment, keeping the astronaut's body temperature within normal ranges by allowing water to circulate through the tubes. Then, our lower torso, leg, knees, and feet. Portable life support system, oxygen tanks 1.5 pounds, 0.5 kilograms at a 518 ATM tank pressure. Carbon dioxide scrubbers, filters, cooling water, 10 pounds, 4.6 kilograms total. Radio electrical power, ventilating fans, and warning systems. Food on Mars. Nutrition facts, examples. Okay, so a mission to Mars will require approximately about 880 pounds of food that they will need to survive. This includes a mix of calories, protein, fat, and fiber. The amount of water it would require would be 456 gallons of water per person. While water and oxygen can be recycled, the freeze-dried food still contains 28% of water, which helps compress. So my example right here, where the food is, it's an evolution of how food went downsizing and going into simpler things for astronauts. And my example over here is the the space food system. So first, I will be touching on that a little bit. I won't touch on it a lot, but I will touch about the most important things to me and to our mission. So, the food system must be free from microbiological, physical, or chemical risks to astronauts. We need this to be right because the safety of our astronauts is very important. Nutrition. The food system needs to provide adequate nutrients while avoiding nutrient toxics. Usability. The food system must account for the human factors and must be user-friendly. And then stability. Stability. The food system needs to provide nutritional requirements and platability through 5 years of deep space conditions. This, since our mission is 12 months, that really doesn't apply to 5 months, but that is just an example of what we need for our food on Mars. So our spaceship. So our first spaceship right here, where it says original, is our first spaceship, which was a little just simple in our opinions. When me and Brianna were working on this, we were evolving and researching everything. So carrying capacity. After a minute, so this was the portaloid system, the guidance system, and then the opposite reaction of, I'm sorry, I can't say that. But after all, this was a little too simple and we needed more space to carry all our people. So then we switched to our second original, which is an example of SpaceX. And this really helped us evolve in a way. So this is an example and like our own creation at the time. So we have the wrapped and ender, which we added after we did that, and the fuel turbine, and then the logs turbine. This was a very situated thing that we needed to work on a lot. There's an example if you want to read more into it. And then over here we have our power source. And then it's the nuclear reaction, the nozzle, the control drum, and many more. This is also very important to us because we needed a power source to have us go to space. I will leave it up for a little more for you could get more of an example and you could read a little more off of it. Okay. Communication system. The radio link communication, radio wave signals. Since they're satellites, we could use that to communicate in laser signals. Built-in computers on aircraft will be necessary when building the aircraft and for our astronauts. On Mars compartment, space station. So this is the station we chose. The Van Thunberg Air Force Base. Air Base in Santa Barbara County, California. It is one of the largest Space Force bases and it's one of the largest ones. And then it is 98,000 acres of land. Space traveling. Dangers. So our space traveling dangers are radiation. Radiation is very harmful because there are many particles from the sun and there are other cosmic sources that can damage DNA, increasing the chances of cancer, which is very not good. Microgravity. Microgravity is very harmful because of the lack of gravity. It can cause bone and muscle loss, cardiovascular problems, vision changes, and fluid redistribution in the body. The long time spent on the mission can get lonely and can cause psychological problems, sleep disturbances, and behavioral issues. The environment is very different, and there will be a vacuum space, extreme heat situations, and potential for I can't say that, I'm very sorry, but it's right here, micro impacts. There might be big fails, like equipment might break down or even just human errors. Other than the effects of radiation, microgravity, and isolation, there can be effects like kidney stones and compressed immune systems. Space dust can be a major issue that is prevalent throughout space. It can be damaging to equipment and to human health. These are our space traveling dangers we have to look out for when traveling and we have in mind for our mission. Thank you for listening to our presentation. Again, very sorry Brianna Chavez wasn't here, but she will be here for the next time. Thank you. And yeah.
Okay, everyone, that is that presentation. I am waiting to hear. Okay, so the next group is coming in 10 minutes, so just stand by. I will pause the recording, take a stretch break, and I'll see you all in 10 minutes.
Excuse me, Nicole, do you think I can send the slideshow to you and then you can present it?
Sure. I could see it just fine.
Yeah, because I realized there was my note doc that I needed to have on my screen. Um, is that okay?
Sure. But I mean, do you have another team member that can do that? I mean, I can do it, but whatever you want to do.
Okay. I think I just shared it with you.
Okay. Can you see it?
Yeah.
Okay.
Okay. Hi, this is Project Aries. and this is our slideshow for our mission to Mars. Starting off with the contents, we're going to go through a few different aspects from the mission details, the human team, our habitat, our ground mission, including the rover, and then the agriculture at the end. Julian, do you want to do this slide?
So for the mission, we will spend approximately 1 year and a half on Mars. We will be landing at the Jezero crater. We won't have a resupply ship coming because our mission will be self-sufficient, as we'll be growing food on Mars. We will communicate through already existing Mars orbiters, and all our things will not exceed 30 tons, and our launch window is 26 months.
Yeah, and we're also going to use Mars orbiters, including Maven, the Mars Reconnaissance Orbiter, Mars Express, and the 2001 Mars Odyssey in order to communicate with Earth.
Keeping humans entertained is a very important aspect of our mission as it boosts morale. And since astronauts are going to be far away from home, this is a very key aspect of our mission. Since this mission, we will have a digital media hub that we will take with a preloaded server that comes with movies, games, ebooks, music. This weight is approximately 20 kilograms. This is going to be shared between all 4 of our astronauts. We will have 4 multimedia tablets that they can log their research on. These are weighing approximately 5 kilograms each. Keeping our astronauts fit and healthy is also one of our top priorities because this helps them stay happy while being far away from home. We will bring the Colbert, which is currently being used on the ISS by astronauts. It's a treadmill using small vibrations to simulate running on Earth. The second machine we'll be using is the cycle ergometer and vibration isolation machine, or CEVIS. This is a stationary bike. The Advanced Resistive Exercise Bike, or ARED, is used for weightlifting. These 3 machines are going to be key in helping our astronauts stay fit and de-stress from the pressure of their mission. Since exercising is proven to help human de-stress in the astronaut schedule, they will have a set time every day to use these machines. One of health and roles of our astronauts. One of the astronauts will be a doctor/biologist who's conducting research of the effects of Martian life and also life in space on the human body and life in general. The doctor will be performing research on the other astronauts and themselves, as having them doing different exercises. Every day they have their certain routine, which includes exercising using the machines we just talked about, and they'll also take medicine to make sure they don't get sick from space radiation. Astronaut 1 will be the commander, who is a scientist and biologist. Astronaut 2 is a geologist and paleontologist. Astronaut 3 will be the doctor and engineer, who will be doctor and biologist, sorry. And astronaut 4 is the astrologist and physicist. We've chosen to use NASA's XEMU, or Exploration Extravehicular Mobility Unit, which offers improved mobility, durability, and life support systems tailored for planetary exploration such as Mars. This is their spacesuit that they will be using on the Artemis missions. For surface operations on Mars, the XEMU is ideal due to its enhanced range of motion, dust-tolerant design, and ability to handle the planet's lower gravity and harsh environment. The suit weighs approximately 125 kilograms, which for 4 astronauts is around 600. This suit is critical for astronaut safety, enabling long-duration EVAs, extravehicular activities, while protecting against radiation, temperature extremes, and abrasive Martian dust. On the right, we have a picture made by NASA that shows all the features of this suit.
Okay, now we're going to talk about the habitat that we're going to use. So this main hab is where our astronauts are going to live and stay for most of the mission. So it's really important that it's safe and can withstand all parts of the Mars atmosphere for our year-and-a-half mission. So the main shell will be made out of carbon fiber, which will make the hab more lightweight to bring over and also very durable. And we're going to use the full 8-meter diameter for this hab. On the inside, on the outside, we're gonna have a Teflon coating that will protect the hab from the Martian environment and UV because it's a dust-resistant polymer. On the inside of the hab, we're gonna have an aerogel layer, which will act as insulation and also help conserve energy for the hab and the environment inside of it. And then in order to block radiation, what we're going to use is plasma magnets, which is kind of a newer technology, but within 10 years, it's very plausible that it will be crucial for space missions similar to this. And basically what plasma magnets are able to do are shield not only a small area from radiation, but it is also it's going to actually shield a larger area outside of the hab, which will be beneficial for not only is it extremely lightweight, but it can protect the entire area from solar particles and flares. So it'll basically nullify all the radiation effects on our entire crew and their whole area that they're going to be working in. Next, what we're going to use for power is a fission reactor called Krusty, which is a kilopower reactor that is powered by highly enriched uranium-235. And the reason we're bringing this is because it'll be really lightweight, and it's also been tested on the Martian environment already. And so we know this will provide more than enough power for our hab and the entire mission to operate successfully. Next, we have our ECLSS, which is Environmental Control and Life Support System. And this system will help regulate humidity, temperature, and CO2 inside the hab, and also help with air circulation. So it's basically just a pretty normal life support system. Next will be our water reclamation system, which will recycle all available water using urine processors, water filters, and purifiers for existing gray water, for example, from showers and stuff like that. And then also a humidity condensate collector. And afterwards, after the water goes through the system, it'll be 100% clean and usable. And this system does reclaim about 90% of the water. And then finally, for oxygen generation, we're going to use a system very similar to MOXIE, which was the Mars Oxygen In Situ Resource Utilization, which has been proven effective at converting CO2 into oxygen in an experiment done on the Perseverance rover. So what we're going to do is try to scale it up a little bit to create plenty of oxygen for the entire mission, because it's a very key gas that we're going to need to use. And then for all these essential systems, such as life support, water reclamation, and oxygen generation, we're going to have backups to ensure everything stays safe. And this diagram on the right is basically just a image of how the space will be partitioned. So like Julian said before, some of the like exercise machines and stuff are going to be in the quarters. The shared, a lot of it is taken up by the airlock. And then you have sleeping pods and obviously the lab, which is really important to our mission. Next, we're actually going to have a secondary hab. So this is going to be used primarily for growing crops for our Marsonauts to eat. And the shell for this lab is going to be made out of Vectran, which is super strong material. but it is still inflatable, which is really important because we want our hab for crops to be a good bit larger than our normal habitat, so we can have like a larger area to grow crops and be more efficient in our food. But this Vectron will also be able to protect the entire greenhouse from the Martian environment. And then our crops will also be grown hydroponically, and we will have more details about the crop growth towards the end of the presentation. And then for radiation, like I said before, because the plasma magnet is able to cover a large area, we don't need to worry about radiation for the secondary hab. And we'll also have 3 racks inside of this hab for more efficient growth of the crops. And then finally, all the atmospheric power and water needs will already be satisfied by previous systems that we talked about in the last slide. And the CO2-rich Martian environment will also help speed up the growth of crops compared to Earth's atmosphere, as having 2 to 3 times more carbon dioxide present actually helps them grow more. And then this diagram on the right is kind of what it would look like. It's not a perfect image. Obviously, the sides will not actually be transparent. That's just so you can see what's inside. And then there will most likely be LEDs inside to simulate sunlight instead of actually, having it be transparent. Okay, so next we're going to talk about our ground mission. These are just some images of kind of what it will look like. So our first thing is the ground vehicle that we decided to use was a hovercraft. So we've chosen an air cushion vehicle, or ACV for short. And even though this kind of looks like a science fiction looking device, all aspects of it are actually truly fully grounded in reality, and they've already been achieved. So this design was chosen because given our landing site near the Jezero crater, our terrain will mostly be flat ground with dust and smaller rocks surrounding. And this design allows us not only enhanced speed from a regular wheel propelled rover, but also for many less moving parts to be exposed to the dust that will eat away at most Mars craft's joints and bearings. So this vehicle will be powered by solar panels lining the roof, and they're not created to scale the model, but they will be capable of housing 2 crew members at a time. And the pressurized design with onboard oxygen, synthesization, and stored food and water means that this craft can be piloted without a spacesuit needed. And inside of this hovercraft will be kept all needed experimental equipment. And it will also be made from light composite materials and have backups for both the skirt and the propellers. And one of the main advantages of having this hovercraft, like we said before, is it will be less susceptible to the dust, and also it'll be able to kind of go over any rough terrain because of the frictionless surface on the bottom, which will allow for much easier transport. Now I'm going to talk about the aerial surveying component. So after Ingenuity's first flight on Mars, the possibilities for flight on Mars have opened up a whole new aspect of what is possible. Even still, it is very easy to get carried away and include impossible features for a drone on Mars. And because of this, we'll be staying very faithful to the original design, only scaling it up to 3 halves the original size and including 2 additional features, which are LiDAR scannings and long-wave radio broadcast. So this will be enormously helpful on the mission, and before any ground missions take place, the surrounding areas will be scanned and a 3D model will be transmitted to the ship by these aerial surveying components in order to adjust or improve planning for the mission. Along with this, they serve the function of essentially being dust cleaners for solar panels, outside parts of the hab, or even each other, given that 4 will be brought along with 3 active and 1 extra. They will charge on rooftop contacts that will hook into the landing gear for the drones and charge from the main nuclear reactor. And one big advantage of these are they're going to be super lightweight, so it'll be extremely easy to bring them, and the value that they add to our mission is a lot. Next, we're going to talk about spacesuit. Julian kind of talked about this a little bit before. So yeah, this is just a quick overview. You can see some more images that we have. Okay, yeah, and next, Caitlin's going to talk about experimentation and sample collection.
All right, so for experimentation and sample collection, we'll use ISRU for collecting soil, water, and CO2 from the atmosphere and analyzing that back on Earth. We'll also look at meteorology and use sensors to measure wind speed, temperature swings, and pressure changes over time. And then we'll also monitor radiation on Mars. We'll need to travel to crater rims and impact sites for exposed subsurface layers, like finding water that is below the surface, and then mid-latitude regions.
For the agriculture, this plan supports 4 astronauts for a period of like 1.5 years on Mars with a total food-related payload of under 2 metric tons. The crew brings 30 days of food that's like prepackaged, including freeze-dried and air freeze. That while they're setting up the secondary hab to grow crops. Then they'll transition around Sol 31 and Sol 30 to hydroponic food production using recycled water and the systems that we've installed in the secondary hab. This also includes an emergency buffer and spare margin. If something goes wrong with like growing the crops in the secondary hab, they still have another 31 sols left of food to survive per astronaut. Over in the bottom, we have the mass budgets for each of our categories. So for the first 30 days, it's around 0.22 metric tons. That includes freeze-dried meals. For all the crops, it's only 0.01 metric tons. And for the systems and all the growing things we're going to need to grow our crops, that's around 1.120 tons. So the total mass allocated we have is 160 tons. The total mass of all this is approximately 1.6 tons. For what they will eat, we will be growing potatoes as those are core calorie sources. Sweet potatoes provide lots of vitamins and carbs. Soybeans are very good for protein, which they're going to need. Lentils are also a secondary reliable source of protein. And greens to keep them healthy. The tomatoes are there for a variety of food in case they get bored of the other ones. As William already said, all our crops are going to be grown hydroponically. What that means there's no soil, just lots of nutrient-rich water that's being circulated in the ecosystem. This means we're going to have to use a lot of water. That's why we have a water reclaimer. For the daily diet, this on the right, we have this consists of what they should eat approximately within their 3 meals spread throughout the day. So 1.2 kilograms of potatoes, 0.5 of sweet potatoes, 2 kilograms of lentils, 0.3 kilograms of greens, 0.2 kilograms of tomatoes, and 0.05% of oils to cook these foods. So that rounds up to approximately 2.7 kilograms per person per day, or that's 3,000 like 200 calories per day. This is more than the recommended amount by the United States Food Administration. For farming begins on Sol 21, and all of these crops are selected for efficiency, quality, and nutrition. Emergency food covers 1 month, and that means that's enough for them to start up the hab again. Thank you for listening to our presentation.
Thank you so much. We are waiting for Team Young Sheldons. They have 4 minutes to arrive. They are scheduled to be here and say they will be here. So in 4 minutes, we will start with Team Young Sheldons.
Thank you.
Okay, thank you very much. Okay, recorded screen share.
Are you muted?
No, we can hear.
Oh my gosh.
Okay, this is our presentation from Team the Young Sheldons, the missions to Mars. We're going to first start off with engineering.
So for engineering, our goal is to build a sustainable habitat on Mars for 6 astronauts so they can survive 1.5 years. Some of the biggest challenges with this are radiation, dust storms, temperature changes, life support and integration, and launch load. When it comes to habitat types, there are 2 main types. There's above ground and below ground. With above ground habitats, they're easier to access and construct. But some problems with above ground habitats is that they have higher radiation exposure compared to below ground habitats. And to combat that, you need heavier shielding, which increases the launch mass, and they're more vulnerable to dust storms and temperature changes. With below ground habitats, some of the pros are that they have a natural protection against radiation, micrometeoroids, dust storms, and thermal swings. They also use local regoloth for construction and shielding, which reduces launch mass significantly. Some problems with this, however, is that it requires excavation equipment, and there are also risks of cave-ins, and there's no natural sunlight for greenhouses if we were to set them up. For our habitat design, our structure, we made it so it's 2 to 5 meters deep for radiation and thermal protection. And then for a single pod, we made it 15 feet tall, 8 feet wide by 20 feet long. Our habitat layers consist of an outer layer of basalt fiber reinforced Martian concrete, printed in tiles to provide structural load bearing, integrity, and shields against radiation. For our internal frame, we made out of aluminum lithium alloy because of its lightweight, durable. It distributes internal pressurization loads evenly. And the inner hull, which is made from a Victrin Kevlar composite fabric for pressure containment. And then finally, an insulation out of aerogel and foam insulation because aerogel is very lightweight and has low density. For construction excavation, we plan to use 3D printed Martian regoloth, as I said earlier, for the tiles in the outer shell. And this reduces the launch mass and improves durability. For our excavator, we came up with the caterpillar excavator design with 3 axes, with an interchangeable tools, an auger, a bucket, and a grabber, with a max dig depth of 3 meters and a max load of 200 kilograms. Our power source for the excavator would be solar panels, and our power storage system would be lithium sulfur batteries because they're high energy density. For power systems, our primary power system would be an RTG. It uses plutonium 238, and we chose it because of its reliable baseline power. And one thing to keep in mind with it is its strict handling precautions because it's radioactive. Our secondary power systems are solar panels and wind turbines, but we have to keep in mind that solar panels are limited due to dust and low sunlight. And for energy storage, we chose the lithium sulfur batteries again because they're high density and they're lighter batteries, and LEP batteries because they are safer and have a longer lifespan. When fully charged, we'll be able to supply the habitat for 24 to 48 hours. For our life support systems, we went with a primary 2 electrosys units, which will produce 79 liters an hour each, which is enough for all astronauts on all of the crew. And for backup, we chose 2 MOXIE units, which will produce 12 grams an hour. For water, we chose internal storage tanks that will hold about 3,000 liters. And for extraction, we chose a drill and evaporation plus condensation hopper. Recycling, we would recycle urine and have a gray water filter. For air temperature control, we plan to have fans and ductworks in the walls and underneath the habitat to mix up the air and make sure there's nothing getting left behind, get everything around. And liquid cooling loops and radiators to control the temperature. For our airlock module, we chose the NanoRack Bishop airlock. We used a modified version. It's the same one that's used on the ISS, and it would be about 6 meters in diameter and 6 meters in height, 6 feet in height, sorry, with a mass of about 2,300 pounds. And then inside of that, we'd also use electrostatic curtains for dust mitigation. For our rover design, we chose a lightweight open frame rover. It would have no pressurized cabins, and astronauts would have to operate it in suits. It'd be a 2-seater chassis with a titanium carbon composite frame to save on weight. And it would use lithium sulfur batteries again because of their properties, and a solar panel mat to charge them. We would keep oxygen and water easily accessible through the suit by using hydration ports. And it would be a 6-wheel electric drive with brushless motors. And there would also be tool storage and emergency gear on the rover as well.
Yeah, I know. Sorry. So, Mars's environment.
Hold on.
Turn it down.
Yeah, there's somebody needs to mute because there's a lot of background noise.
There we go. Okay. So Mars's environment, its atmosphere is about 96% carbon dioxide. No. Okay. I'm sorry.
Are you there? We can't hear anything.
Here. Can you hear us now?
Yep. There's a lot of background noise because 2 people are unmuted, so somebody needs to mute.
Okay, I think this works. So Mars's environment, its atmosphere is about 96% carbon dioxide. It also has about 2% nitrogen and 1% argon. It also consists of other elements, but they don't really matter too much. The gravity is about 1/3 of Earth's, so it's about like 3 meters per second. Negative 3 meters per second, I'm sorry. The temperature is 70 degrees Fahrenheit to negative 225 degrees Fahrenheit, which is negative 143 to 57 degrees Celsius. This was important because we needed our equipment and machinery to be able to operate in extremely cold temperatures. The solar radiation is about 240 to 300 millisieverts per year. For reference, Earth's is about 4 millisieverts per year. The day length is pretty similar. It's less than 40 minutes longer than Earth's days. The year length is 687 days, and it has much harsher weather.
With Martian's environment, we decided to create our science objectives surrounding what is currently unknown. For our 3 top ones here is astrobiology, climate, and geology. With astrobiology, it's a study of biology in space. We're going to primarily focus on microbiology. For climate, it's a study of weather patterns using modern technology and history to predict future weather events or understand the evolution of Earth. Then geology is a study of mineralogy and the history of rock layers along with paleontology and much more, and finding materials that we can use like gas and oil. But the question is, why? We decided to choose these science objectives to first figure out what's going on Mars to be able to, for future missions, so we can understand what's there currently instead of focusing on its past. Continuing on, our science equipment for astrobiology is a GCMS, the Agilent 7100 CE microcapillary electrophoresis system, the wet chemistry lab from Phoenix, and a solid immunoassay detection of small chain and complex organic molecules. We chose these instruments to be able to find the right molecules that are in organic life, such as microbes and isotopes. For geology, we chose the ChemCam from Perseverance, the SuperCam from Perseverance, the MassCam from the same rover. Then our other instruments are the X-ray diffraction, the Raman spectroscopy, the mass spectrometer, and the Fourier transform infrared, also known as FTIR. These were especially chosen to search for the types of mineralogy that is related with our landing site. For climatology, we're going to be using the META from the Perseverance rover and the REMS from the Curiosity rover to be able to detect the wind and atmospheric pressure from the spot we chose. So with the spot we chose, it's Arcadia Planeta. We chose the spot because it has a presence of accessible ice nearly inches away. It has a diverse area of minerals, which gives it color, also known for its very colorful pictures. It has an active amount of wind because it's an area that is known for geological changes and shifts throughout the billions of years. It's near young volcanic rock that, from what I remember, 3 billion years old. It is a flat plain that allows a safe landing for our ship and habitat to work. And it's considered one of the few most safest landing zones across Mars. For our communication tools, we decided to use relay satellites because they are able to process more data at high resolutions, allow more data to be transferred more often, since there are currently orbiters such as Mars Odyssey, Mars Atmosphere and Volcanic Evolution, ExoMars Trace Gas Orbiter, and Mars Express, making it a reliable network for which we can contact the people that we have on Mars. And to access the satellites, we're going to be equipping our rovers as well as habitat with high gain antennas for direct communication with Earth. Although the key takeaways from relay satellites and overall communication with Mars, it takes time to receive messages since it's around 6 months away from Earth. However, by using these relay satellites, it allows for reliability and connection. Next is human operations.
Moving on to human operations and factors. Our goal is to identify challenges and consider solutions of daily crew life in concern to the 18-month mission, which includes the crew members and qualifications, their behaviors and routines, as well as entertainment, clothing on Mars, food storage solutions, and the psychological effects of living on Mars. Now, the crew members who will maintain the habitat stable and work on both technical, communication, and psychological issues during the mission are as follows. The mission commander, who is going to overview the operations of the mission, as well as the progress toward the mission's scientific objectives, and will also act as a leadership figure who helps with the collaboration between crew members. The mission specialist will aid in the production of experiments and the coordination of the mission, as well as help with the operations of the habitat systems and technical issues. The engineer will help monitor and operate technical systems of the habitat and assist in mechanical issues. Now, moving on to the scientist-astronauts who will help complete our scientific objectives. This includes the astrobiologist, astrogeologist, and the planetary climatologist. These people will help in fulfilling our scientific objectives and research in astrobiology, astrogeology, and planetary climatology. During the stay of the astronauts on Mars, they will regularly consume specially packaged meals such as protein packs, freeze-dried foods, and powdered beverages. These meals will either be shelf-stable or be heated and rehydrated utilizing purified water. Astronauts may also utilize hydroponics to boost morale and nutrition by growing their own food, and they may also eat meals as a group to strengthen social bonds and promote mental health. Every astronaut will also sleep in their own separate soundproof pod that will help replicate the night cycle as found on Earth, especially since all astronauts need their sleep. These astronauts will also participate in regular exercise to maintain both mental and physical health and combat bone and muscle loss. Now, entertainment during the space mission. We will have to ensure the compatibility of the crew members through socialization, and the astronauts will also contribute to the flourishing of the greenhouse, which may boost morale and act as stimulus other than those provided by scientific research and problem solving. And by maintaining communications with Earth, they will also provide entertainment. Now, one of the most appropriate fitting spacesuits for our mission could be the Exploration Extravehicular Mobility Unit (XEMU), a type of EVA suit that provides the benefits of a cooling garment for the regulation of body temperature, and it contains a very appropriate life support system, a nice communication system, and the overall suit provides sufficient protection from radiation, extreme temperatures, and dust and debris.
Now for food systems, storage, and growth. For food systems, we plan on utilizing a mixture of prepackaged food products and the growth of our own produce through the usage of greenhouse during the 18-month-long stay on Mars. Prepackaged foods may range from, but are not limited to, freeze-dried items, thermally stabilized food products, powdered beverages, protein packs, and /meat, soy options. We can utilize design compartments of the habitat to maintain food quality. These compartments will keep packaged items safe from Mars dust and contamination while also storing the products at ideal temperatures and making sure that they are not tampered with. The lack of atmosphere could also damage the prepackaged food if exposed, as the food could experience great temperature fluctuations and mess up or ruin the quality of the food. The main growth system that will be utilized for the greenhouses will be hydroponics, which uses nutrient-filled liquid and substances other than soil for support in growing plants and vegetation. An example for an ideal greenhouse would be the 30 by 48 hydroponic grower package from Rimo Greenhouses. A similar system, such as the vegetable production system found in the ISS, could be a viable option for growing food outside of the Earth as well. Food systems and storage, our nutrition plan. Portion sizes. These are the daily portions per meal that we have calculated. For breakfast, for an example, we'll have 250 grams of oatmeal plus 50 grams of nuts and fruit, and usually we'll have freeze-dried pasta, veggies, protein. It'll be balanced, and it'll all come out to 2,500 calories per person per day. It accounts for the activity level and microgravity effects as well. So the total count will be 8 million calories per day. And the total weight estimated will be 1.9 metric tons of food for 6 astronauts for 18 months. And if we add an extra 15% for emergencies, spoilage rates, and morale boosts, it'll equal 2.2 metric tons of food approximately. So we will need 2.2 metric tons for 6 astronauts over the course of 18 months. The various types will be freeze-dried meals, proteins, grains, fruits, veggies, nuts, and treats to maintain a balanced diet. This is our pie chart that depicts the variety of food that will be available to the crew members during the duration of this trip.
This concludes our meeting. So is there any questions that anyone would like to ask?
Is that it?
Yes.
Okay, thank you. We are.
Screen share wasn't on. I thought you guys were done. It's not allowing us to share.
It should let you. I haven't changed anything. Oh, there it goes.
Okay.
And definitely lastly this time is the psychological factors in the Mars mission. Psychological isolation. Astronauts may experience severe psychological effects from isolation on space missions, such as those to Mars. This is not limited to, but may include feelings of homesickness, rise in anxiety, emotional exhaustion, mood swings, unusual light cycles, and stress can interfere with sleep as well. impairing concentration and judgment. Living close to the same people for months can lead to group tension, and astronauts may become cognitively exhausted and lose motivation in the absence of variety or stimulation. During participation of analog missions simulating Mars, the design team may collaborate and work together beforehand to increase compatibility and help diminish the effects of social isolation, such as a test run or doing something to simulate the situation for a while so they could have a feel for the environment before taking part in the mission. Ethical scenarios on Mars. Mars crew emergencies will most likely be dealt with by the mission commander. All should obtain equal resources, whether that be in food or equipment, what is necessary for the mission, to help avoid conflict and rising tension. AI team members are vital towards the success of the mission. Analog missions prior to the Mars mission may help aid with finding solutions to any possible ethical issues that may arise during the mission. Thank you very much.
Thank you. I am still waiting for Team Star Club. Is anyone here from Team Star Club?